about binary interactions fundamentally, but I will bring observations to bear quite heavily because I think this, as everybody here is a phantom simulator or a theorist, and I think we forget all too often how important that is. We all say, but nobody, well, most people don't do it well enough. So this is the students you've met. Some are sort of shocked on the bodies of other people, but it's just not everybody was there. And in fact, I really should thank them first and foremost, because particularly in the last 5 years, I've been extremely busy with, let's call it the more political side of astronomy. And without them, I would have just sunk. No. Okay, so very, very simple outline. We'll talk about this one specific interaction, the common envelope. It's got a oddly technical name, but it is a fundamental thing in pretty much all binary interactions one way or another. And today, with transients being a thing, and even more of a thing with Rubin, this particular theoretical niche, which used to be quite unstudied actually, is becoming more prominent and important. And I will talk about cool objects that can really validate our simulations. So to give you an idea of what this thing is, this is from the thesis of Thomas Reichardt. It's basically you got two stars. They're happy until one grows fatter and fatter. It fills its Roche lobe, moves mass onto the companion, which is usually more compact, main sequence white dwarf or neutron star or even black hole. And that transaction is catastrophic in that at first the mass transfer is conservative and stable, but then you get outflows from L2 and L3 that shrinks the orbit even more and tends to move it into a catastrophic regime where new forces such as hydrodynamic friction and gravitational frictions take over, and you get an in-spiral of the companion in the envelope of the primer, usually that way, or the two envelopes merge, and you end up with a compact binary that either manages to eject the envelope and resist, so you have your compact binary coming out of it, or you have a full merger inside the common envelope, and then you have one star. Now, it is a very hard problem to simulate because it has a great range of both time scales and size scales. Indeed, any object can do this. Massive stars do it, low mass stars do it. So you really could have anything from, a few solar radii in size for the primary to 1,000. You can also you're going to have to model the orbits. You have to model that scale as well. And of course, the time scales go from the period of large orbits to, minutes of things that happen near the core. So it's been traditionally a complicated problem, but it has also been in the olden days, it was kind of a niche problem because it seemed to explain the existence of a handful of curious objects, but not mainstream objects. However, if you actually look at the range of objects that the common envelope is necessary to create, there's quite a few. Of course, you have the X-ray binaries that have gone through one or two common envelopes and will yet go through at least one. So this is a very big event in their life. You have cataclysmic variables where the white dwarf and the main sequence stars are so close that they must have been inside the orbit of inside the progenitor of the white dwarf when the white dwarf was a very big giant. A lot of central stars are planetary nebulae. In fact, at least 1 in 5 is a post-common envelope object. That's actually how I entered this field from planetary nebulae. Luminous red novae, they used to be few and far between. We have a lot today, and will be central to my talk. But they also produce things like double neutron stars and double white dwarfs, which eventually go on to merge with type 1a supernovae or kilonova events. We have a whole new fields of planets going to stars. Stephen here, who decided not to give a talk despite my best advice, has been working on that. And of course, there's a few others that will come up as Rubin discovers more and more events. So the simulations that have been done, it started very few, and now there's quite a few groups doing it. But interestingly, it's kind of all we had for a long time. Because the common envelope is a dynamical event, so it's a transient event. And when we didn't, have the resources or the technology to look at transients, we just didn't see them. So simulation, I have actually my old students writing in the introductions of their papers, we can't see them, so might as well simulate them. So in fact, this was the landscape when I came in. So there were the black and white simulations with the contours. From Ron Tam's group, this was mostly a grid simulations. There was this excellent paper from Razio and Livio with SPH, I think like 50,000 particles. and a little bit of trickling of more modern stuff coming from Paul Ricker, who was using Flash at the time. Interestingly, this old papers with really what we would judge today poor simulations are excellent reads because they made up with wisdom what they were lacking with technology. Anyway, I came in at around 2000, being very curious about the central source of planetary nebula in post-common envelope configurations. And I talked to Eric Sandquist in the TAM group, and he gave me his code. His code was very was clunky, and there were a lot of problems. So I moved on using ENSO. And when I came to Australia, I had my first PhD student, and with Jean-Claude, we adapted ENSO to the common envelope problem and had a very good simulation. But since then, a lot of groups have started because with transients being observed now routinely, of course, this becomes a much more tangible problem. There's a lot of groups using all manners of codes. Most groups do some tricks. So, for example, they may not resolve the orbit. They keep the orbit fixed and understand how that interacts with the envelope of the star. But there are also groups that do global simulations, meaning a free orbit with a proper star, usually one instead of two stars. And there's Natasha Ivanova with Star Smasher. There was an interesting attempt, but I think they completely died out. Changa, this was a moving mesh with Charm++, weird CPU, GPU interfaces. Morgan McLeod, my bet is on him solving the problem. He's a fantastic researcher. If you ever read papers, he's a fantastic, really, really good researcher, very broad. Uses Athena++, but many other codes as well. The Israelis, Guy Peretz and Noam Sok are doing quite a bit. There's AstroBear in the US with Adam Frank. And then, of course, probably the powerhouse today is the HITS group at Heidelberg with Fritz Röpke using Aripo, who's a moving mesh code. So that's great. That's what you want, right? You don't want to be on your own just because you're first. Your first bet is crap. You really need a lot of people around to talk to, and hopefully they talk to you. So my first simulation was in 2012. That was the paper. And since then, what we have gathered with all those groups working has really been a handful of things, mostly because the simulations take so long to do that you don't do parameters coverage at all. We mostly been doing Loma stones with Mike Lau with Phantom having done the first good, a higher mass star simulation across solar masses. The secondary is always a point mass, which is a bit of a shame, particularly if it's a main sequence star. We do a lot of ad hoc experiments. These are fun. They give you a nice paper, but they maybe not be too consequential. There's a lot of unknown problems that are hidden in these papers. Eccentric orbits, triples, planet companion, jets. So this was the idea that if you develop a jet, so Anne has been working on this as well, outside the common envelope, that jet goes into the common envelope and may do some damage. And we found that it tends to, but these jets are very unreproduced from primary conditions. They are basically ad hoc placed there, and then you look at what it does. Magnetic fields, there's only a simulation, or maybe a couple of simulations to date from the Heidelberg group. So the magnetic field does develop. We had just a talk about the MRI. So it's supposed to grow quite well and become a global magnetic field that can impact the ejection itself. So this is certainly something that will be very important in the near future. However, these simulations are slow, they have limited resolution, they have limited physics, they have limited physical time. So we tend to do the dynamical time a couple of decades, but we really would want to know what happens in the next couple of centuries. And they don't do parameter space explorations because of the time it takes. So a good higher resolution simulation will take a few months, right? So what we have been able to determine, despite all the shortcomings and difficulties, is we've started to understand what the final separation after the common envelope in spiral is, including what type of objects lead to mergers and which type of objects emerge as binaries. And this is really important for the reasons I'll explain shortly to try and feed information into population synthesis. We understand the ejecta masses. We're starting to understand the dust that is produced in common envelopes, which is what we have done in the last couple of years. The photospheric size of the common envelope thing that emerges from the spiral is critically important because perhaps is one of the few things we understand reasonably well. And I'll show plenty of things we don't understand very well. And more importantly, we finally know how to eject the envelope. When I started, you had a common envelope, and then you looked at your envelope, and it's so lifted and it expanded, but it's not ejected, which means you never emerge from the common envelope. The prediction from simulations for the longest time was everything merges. So this is actually a few solved problems. On the right here, we have separation versus time. This is the typical in spiral shape. It changes a little bit when you change equation of state, but fundamentally, you don't have very big differences. But the thing that's very different is in the top, the yellow line shows you that the mass is not unbound when you use recombination energy via the Mesa equation of state that Ali has plenty of experience with. You do eject the envelope, which was a very big result. Okay, so with these simulations, with the knowledge we've gathered so far, what do we do? Well, the people that really stand to benefit the most are those who are modeling full populations of binaries in a galaxy, let's say. What they are interested in is explaining all manners of things, period distributions of binary classes, birth rates of binaries, outburst rates, delay times, that's the time between star formation and supernova. So there's a whole bunch of things the population synthesis people target that are reliant on their input parameters. Now, a population synthesis models everything, right? They from star formation to stellar evolution to binary interactions, and all these elements are parameterized with little gizmo formulae, which they come across by looking at simulations and observations to try and refine that. So the whole bunch of things in the recipes include the mass transfer recipe. So if two things have mass transfer, what happens next? Oh, they go through stable mass transfer and then they separate. Or they go through a common envelope and the final separation is such and such. So here you have a typical evolution of one single system from some combination of parameters at the beginning and evolving through various phases of mass transfer. And the boxed out ones are the two common envelopes for that system. And as you see, the common envelope here reduces the separation from 318 to 5, and then the next one from 5.6 to 0.5. That reduction is in the hands of a formula. And the formula is, we have proven over and over that is anybody's guess. And with the simulations in theory, you're helping to understand that. The exact number here tells you what the object becomes. It can merge, it can become a double neutron star that has gravitational waves. So it impacts everything, impacts the rates of gravitational wave events. So it is kind of an important thing. This is a more modern example. So that I just showed you the evolution of one binary. In this review from 5 years ago, you have, I call it genetic diversity, because I like to think of binary interactions as the crossover that creates something that may not have been there if the parameters had been slightly different. Every egg with two yolks is a common envelope. So you see that the common envelope plays a crucial role in a lot of moments in the evolutions of binary stars. The blue is more massive, the yellow is less massive. So no matter where you look, there is common envelopes everywhere. So to talk about something a bit more specific, leading to what really the holy grail of this field is, which is to get good light curves. A few years ago, we had a grant with Lionel Cis, and we had a postdoc, Luis, who looked at dust nucleation in the common envelope. Interestingly, my primary goal, in fact, I wrote the proposal that way, was to think of dust formation in the common envelope to help drive the envelope. Turns out that the envelope is already driven itself with recombination energy, so there's no need for dust. So dust forms okay, but it's not helping in that sense. So on the right here, you have both the in-spiral and the bound mass, and the two lines are with and without dust, and they're not that different, fundamentally are very similar. So that was okay, fine. Now, one thing that's important to say, this was two simulations with two masses. So we haven't really looked at other parameters, only those two. So this is a tiny little movie of the opacity that shows you how the dust, so where you see there's basically dust formation is taking place. And you see this is on the equatorial plane, it's quite nice, but if you see how much, there's quite a lot of dust formation. There's also an interesting asymmetry. This is the perpendicular plane, so it's a slice seen from the side. And you see quite a lot of geometry change here, which could be interesting for the geometry of the nebula formation that can come from many post-common envelope systems, but we're not going down that rabbit hole yet. The most important thing is these things make a lot of dust. So the dust This is for one of our 2 simulations, starts forming at about 3 years, but you don't see here because of the scale. And it forms fully within 3 decades. Fully means all the dust that can form forms. So you can think of it as a dust bomb, right? This is an explosive dust formation. And then, you know, although common envelopes are not as common as single, well, certainly not as common as single stars and other types of binary, this may well be contributed to the dust production or the dust budget of the galaxy. Now, with the simulations in hand, enters Chunliang. So Chunliang and I have plenty of philosophical discussions about this, and I'd like to transmit to you some of his wisdom primarily, and I think backed up by my older wisdom. And this is just watch what you do. What would you publish? So Chunliang post-process Lewis's simulations by doing the usual. He showed in his talk, you shoot rays into the mix, and you integrate the radiation transport with the usual kernel, SPH kernelization techniques. The way he does it is, well, this is actually gives a good idea, right? But if you look from the right to the left, you go into the gas, and you can look at the opacity. The first opacity is very high, that's the dust opacity. Then you have low opacity here, which is the recombined gas is pretty transparent. And then you have the electron scattering opacity. You integrate, right? So the optical depth, will rise until it reaches about a value of unity. That's your photosphere. In the photosphere, you have a temperature, which will dictate the brightness of the object. So this is basically summarized. Julian produced this movie ages ago, and he's never really shown it since, but I think it's really nice because it shows you the dust production. So this is basically your photosphere at time 0. The reason it's dots is because it's every ray perforates the photosphere, and we put a dot color-coded with temperature. And if you, so the thing will expand, so the scale changes in the plot. So don't look at the size because that's reliant on that, but you really see the dust forming very nicely. So here it forms and on the covers. And pretty much for the remainder of the simulation, you have this expanding and cooling ball of dust, which may have an observational counterpart. I'll tell you in a second. So then you do some integrating of your viewport, and you get these are specific intensities or Sofa-Gratis maps like this. These are the 2 simulations, and as usual, we have a top-down view and a side view. And what is interesting about them, first of all, in the top, you really see the resolution problem. It's those blobs are SPH particles. Another thing that's interesting is that you see there's a lot of variability, and that's because it's so 3D. Sometimes you see in and you see hot, and sometimes you see a blob of dust and you see cool. If you integrate that, you get light curves like this, and these light curves are the part where I say, watch out, because if you publish this, which we're about to do, people say, oh, great, that's the light curve. Now, the shaded areas are one of the sources of error bar. It is one of the sources of error bar specifically to do with resolution, but there's others, which I'm about to show you. Things, though, that are a bit better than the light itself are looking at the photospheric radius, because from observations, you can calculate that, and then you can do a relatively meaningful comparison. Thank you, Daniel, for pointing out a very, very big flaw of the paper. So at first, Chunliang and I had the size of the photosphere as geometrically defined, you know, those little blue dots. And that's great. That's very much what it is, right? Except that's not what observers see when they deduce the size of the photosphere. What the observers see, just look at the left side, which is the polar view, is actually this line here. So very different size, right? I think the photosphere is out there, but the photosphere actually is deduced by SED fitting, right? So you have SED fitting, and you find the temperature, and then you have the distance, and then you find the luminosity, and you find the radius. So the photosphere they would deduce actually declines and then grows. The reason for the 2 lines here is because at some point you get the photosphere dominated by the dust, so suddenly grows, and it's out there, and it's also cooler, of course. So, but this is now something that can be looked at in comparison with observations. Now, let's talk about observations for a second. While the light curve comparison, if we could do it, would be brilliant, there's actually a lot more to observation comparison with simulations. So this is what I have been relying on for the last decade. I come from planetary nebula. Perfect. So 20, yeah? So, what?
You have 10 left.
25.
20.
Oh, yes, but I'll leave. So this is the AGV, post-AGV, and Weber cooling track. These are the objects that the atomium people are studying. That's an old picture, but basically it's the AGV with all its asymmetries and binaries. Eventually, the post-AGV star becomes a pre-planetary nebula, non-ionized nebula, and eventually the central star gets hot and ionizes the object. You can use this very effectively. Now, on the AGB, we have today these two classes of objects, water fountains and extreme carbon stars. These are extreme carbon stars particularly, and water fountains too, appear to us to be objects in the post-common envelope phase, maybe in 200, 300 years later. And if that's the case, we have a great thermal comparison with simulation, because from these objects, we have photospheric radii. Look how big they are. These are really large balls of dust. And we can compare directly, particularly if you can get reasonable timescales from the observations, because we have timescales from the simulation. This is actually a plot from Luis's paper that Chunliang did, just to give you an idea that you have this photospheric radii. Turns out these are the geometric ones, not the observer's ones, but it doesn't matter. The photosphere is something you can compare like for like. I think of my observations as filling a diagram like this. So this is a progenitor mass. And this is time from this is dynamical common envelopes here, this is before, and this is after. So I'm filling this diagram with objects such as extreme carbon stars I just showed you, or red supergiant that I'm not going to show you, and the parameters that they can be obtained from the observations directly that we can potentially compare to simulations. As I said, the next object is the protoplanetary nebulae. These are non-ionized nebulae, and they give you tons of information. Now, there's been a lot of discussions of exactly what they are. What we do know is that non-ionized nebula and the star in the middle is in the immediate post-AGB phase. The stars seem to be single. They've been looked up the wazoo because with this geometries, people said it must be a binary ejection. But they're really, really, really stubbornly single. There is this interesting thing that these jets lag by 100 years, a big dusty torus. So there's some information there on the kinematical ejection. They have a certain ejection speed. They have certain time scales. These are probably a few hundred years, 2,000 years post whatever formed them. And I am reasonably sure these are all post-common envelope mergers. There's a lot of debate. If you go to planetary nebula people, they still think every star is single. But they could be excellent constraints for common envelope. These are the post-AGV binaries that Jack and Kayla have talked about, and many people know because they're very interesting objects with disks. So the binary in the middle must have gone through what Kayla called the common envelope light, and it has a circumbinary disk, which can be measured and can be compared to what we produce. In fact, Kayla's doing just that for her PhD, and really try to find out why this bizarre orbital parameters exist. So we are quite optimistic at the moment that this may be a helpful way. Again, so this is the pre-planetary nebula, and the post-AGV binaries occupy this part of parameter space. And finally, my beloved planetary nebula central stars, that's how I enter this field. You often have planetary nebula like this, with a bona fide post-common envelope binary in the middle, observed. It's directly observed, so you're good to go. And these parameters of these objects are relatively easy to obtain, and there's about 40 of them. So we have worked with this central stars of planetary nebula a lot. This is a random paper from a random plot from a random paper where we're looking at the separations of these observations compared to the observations, to the separations of all simulations on Earth. So this, the colorful dots are all simulations, and the black or red dots are the observations. So we've done a lot of work to constrain ourselves that way, and it's been very successful. At first, this is the only thing actually we worked with. It was the most certain thing. This nebula have jets or collimated outflows, and you can measure those to infer magnetic field. Magnetic field strength that we have relatively good numbers on. Unfortunately, we don't have a lot of common envelope simulations with magnetic fields, except for this one by the Heidelberg group, Paribo, and they've just started doing work on it. Interestingly, and this is maybe another little piece of wisdom, the paper they did, which was fantastic, said 3 things about planetary nebula being explained, but it was rubbish. That comparison was lip service. And I know them very well. And I told Fritz, I said, call me, let me know. I give you a hand. I don't need to be on a paper, acknowledge me. But if there is, these connections are not forged both ways by the observers and by the theorists, we're really dead in the water. So my advice to you young people working in simulations is pick your favorite observer and work with them. It does not detract from your paper, it only adds. And you're all young, you all need to get jobs. So putting each other in each other's papers is a very good thing to do. So we have a bit more coverage of my parameter space. And we come now to the light curve. The light curves like this is a luminous red nova. These are probably common envelope mergers. From these, you can get a lot of beauties, like photospheric radii, ejected masses. This stuff is great to compare. This is another paper on a slightly more massive object. The top panel is light curves. The bottom two are radii of the photosphere and temperatures. Again, excellent terms of comparison. But ultimately, we would love to compare Chun-Liang's light curve directly to the light curve, and therein lies the problem. So these objects are all going to be giving us parameters right here, right? So at the time of the crunch time. So we have these are three light curves. This is a very famous one because we saw the binary, and then we saw a poof, and then there's no binary left. So this is the only observation of a merger where we actually know, we have direct evidence. Another light curve and another one. These two are special to me because they seem to have derived from red giant branch and AGB stars for which we have simulated. All the other ones are massive stars in other galaxies, and usually they are subgiants. They're just expanding. They're almost main sequence stars, but these two are not. So we've been looking at them in connection to Chun-Liang simulations. But the interesting thing that has happened is that when you say, okay, what creates the outburst light? And it turns out even that, we have no idea. Everybody has a different opinion. This paper, which everybody cites, comes from 1D, analytical, and there's a sprinkling of 3D to give a little bit of information. And they say the light goes up because there's a hot shell, and then it impacts a torus. So you have one peak from the hot shell and one brightness from the torus impact. This is the spaghetti junction that they produce. They don't compare with any observation. So a lot of comparison is not done yet. But this is a mess. There's every shape in the kitchen sink. These people say, well, this is MESA, by the way. So you inject energy as if it was a common envelope. And then you say that orbital energy, which is primarily delivered at depth, comes out through convection. So there's a delay of about the overturn timescale, about a year. A year later, you get the peak. So that is it's orbital energy coming out by convection. And then there's people like me and Chun-Liang. So the top is Chun-Liang simulation, the bottom is Natasha Ivanova's. These are the only two papers that I know of that do 3D hydro plus trying to get the light. These light curves, Chun-Liang's paper is basically a shopping list of all the things that are wrong that should be right, one of which is trying to figure out with the APR together with Beth. This paper, with the observations overlaid, really doesn't talk at all about that. There's almost no discussion of the error bar. But the light curve is here, and the observations are overlaid. This is misleading, and I'll show you why. So this is a light curve, and this is Chun-Liang's light curve with made into I-band from volumetric luminosity. You can put them on top by scaling and using reddening appropriately. And you'd say, well, the observation here, the pink, is kind of starting to be good, right? Except, first of all, look at the y-axis. There's 30 magnitudes in there. So any mismatch is huge, right? However, the peak actually matches. And the reason is that the luminosities are very different, but the colors are very different in the opposite way and compensate for it. So you could show this and give a reasonable idea that we're getting there. And instead, it would be misleading. And this is just two plots from Chun-Liang's paper. This is a resolution test, SPH resolution test. So this is the best we have is the blue, and the other one is a factor of 8 less SPH particles. Okay, you judge for yourself. Are we converged? Well, you can't even do convergence tests in this game because you can't do 3 resolutions. This one is two simulations where we change only a little bit the surface particles in the star, which are always kind of going astray a little bit, right? Because the surface is not well reproduced. It's usually about a few % of the mass. Dynamically makes no difference. But for the light, it makes a world of difference. Now, this is not terrible, but look, if you look at this, these are 3 viewports, right, of sort of top side and the other side. Depending on where you look at it, you can have very different behaviors. So when you get our competition putting observations on a bolometric luminosity light curve, I don't think this is actually what you do. Like, it's not wrong, it's not a lie, but it is misleading. And that, to me, is borderline. So we did this with Chungyang. I asked him to put this on top of that just for the talk, or in fact, we did it for a couple of tests, but we're not going to put it in our paper because it is misleading, even if it's not incorrect. So my take-home message is, first of all, that global 3D hydro simulations of this type of interaction have really come a long way. Some of the